Hello, everyone, and welcome to today's graph reading group.
We're once again joined by Guan, and we'll be talking about his mirror diffusion models for generating data on convexly constrained domains. Besides that, Guan, the floor is yours.
So just to double check, can you guys see my screen? Right now
Yep.
I'm in. Okay, cool. Okay, so thanks for the invitation, and also everyone who attend the talk. And just for a quick introduction, so my name is Guan-Horng Liu. I usually just go by Guan, and I'm currently a machine learning PhD at Georgia Tech. And today I'd like to present one of our recent work on learning mirror diffusion model for constraint and watermark generation. Okay. So watermark is a technique that aims to embed undetectable information into generated content in order to prevent unethical usage and also to ensure the copyright protection. And given that generative models has become more and more popular, watermark generation also become an important research topic. And there are two key properties that a watermark needs to satisfy. First is, of course, it has to be as invisible as possible, such as the image on the right-hand side. And secondly, the watermark also need to be quantifiable for detection purposes. And using standard statistical treatment, the null hypothesis is to assume that the image is generated without knowing any watermark rule. And then we have two sources of statistical error. So first is the false hypothesis. First is the false positive or the type 1 error, which refer to image that is not watermark but being detected as watermark. And then we have the false negative error or the type 2 error, which refer to image that is watermark but not being detected as watermark. And these two sources of error are not the same. So imagine that we have a dumb Python program that always report a watermark for every single image. Then obviously this detection system will induce zero false negative error because all images are reported as watermark. However, this classifier will perform poorly on false positive error because there will be lots of false alarming. For a large language model, watermark is typically embedded as some selected token set. And for image generation, however, how to embed watermark to, say, diffusion model is still a rather new topic. There are a few prior work that try to embed watermark by training an additional latent space of the diffusion model, but that typically comes at the cost of generation quality. And the information loss between image and the latent space is also not that quantifiable. So in our work on NERD this year, we propose to consider the watermark as the constraint set. And by that, I mean for each image, we will treat that as a single point in a high dimensional state space. And then we can construct a hyperplane with the normal vector that we denoted by A. So the vector A is the normal vector of some hyperplane. And with that, we can define a hyperplane constraint as a set of inequality, which basically constrain the unnormalized distance to the hyperplane to be within the interval that is lower bounded by this variable b and upper bounded by the variable c. And this hyperplane constraint is the basic element to formulate our watermark constraint set. Because in practice, we will consider a product of hyperplane constraint, and each of them has its own normal vector AI and the distant interval denoted by BI and CI. And so this is the constraint set that we will use to define the watermark. In the sense that if an image satisfies all the hyperplane constraint, then we will treat the image as it is watermarked. So the reason why we are interested in this particular constraint set is because, first of all, we find that invisible watermark can be embedded with high frequency normal vector, such as the orthonormalized Gaussian vectors. And this is because high frequency perturbation in pixel space is often hard to detect for human. In the same way of how adversarial examples are constructed. And in fact, this is exactly how all the prior watermark images are generated. Secondly, we also find that we can achieve very low false positive rate, typically less than 0.1%, by increasing the number of hyperplane. And this is because the probability of the null hypothesis to generate image without violating any constraint decay very fast as the number of constraint increases.
Yeah, Guan.
Yeah.
I'm a bit confused by the watermarking set. So first, for our watermarking stuff, are we given images and then we want to introduce a watermark into them, or do we have a generative model that just we generally want to produce already watermarked images?
Right. I think both are valid, and I'm going to cover how the generation process go in the next slide. So just bear with me for a moment, because I just want to first introduce how the constraint set can be used, like what kind of constraints that serve as effective watermark, and then we are going to move forward to say, okay, now we want to generate image in the constraint set, but that is not it is not directly clear from current diffusion model, and how do we fix that? And
so
that's why.
And the watermarks that we bring in here, so they are defined by a certain, this vector A is just completely, or like very much completely random, and we choose one, and then if we find our image to lie within this constraint set, then we have detected it as watermarked by us.
That's right. Yeah, that's right. So, and that's actually one of the benefit, because like the hyperparameter AI, BI, CI are pretty much user specific, and you can view that as a token. So that means that those hyperparameters that define your watermark or your constraint set are private to other user. So and no, it's hard to replicate, especially because right now we are using high frequency noise as a normal as a hyperparameter.
Yeah.
I saw there's one. Yeah. Someone raised hand.
Yeah, hi. Just a quick question, because I think I haven't understood yet how we arrive at the formulation of this constraint set. So if you could, I think it was one or two slides back.
Is it here?
Exactly. So if you could just comment again, please. Why do we have this constraint set? And what are the constraints in the first place?
Sure. So the constraint set that we define is basically like a polytope in the high dimensional space. So, and the way we construct these polytope constraint set is by first, we have we treat each image as a single data point in some high dimensional space, and then suppose you have a hyperplane, and then you can define like the normalized distance to this hyperplane. Like there's the sign distance toward the sign or normalized distance toward this hyperplane with the inequality that's shown in the right hand side. So that's one of the constraints that you can get from one hyperplane. And in practice, we're going to stack among multiple constraint sets so that we can achieve lower false positive rate. And so the combinations of all the constraint sets where I go from 0 to n is the constraint set that we are going to use as the watermark.
So this hyperplane, sorry, so this hyperplane is really separating between watermarked and non-watermarked images. And now we want to find this hyperplane basically.
Right. And so like if I have an image that satisfy all these different hyperplane constraints, then I'm going to assume that it is being watermarked. Otherwise,
we don't want to find the constraints, right? We just define some random set of constraints, and we know these constraints, and whenever an image falls into these constraints, which is very unlikely unless we specifically generate an image to do that, then we know that it's watermarked by us.
Right. So the watermark, like these kind of constraint set is if you have an image that violates those constraint set, and if you project the image into the constraint set, the watermark image is like indistinguishable from the original image, and that's what we want because we want the watermark to be invisible. And so then the question becomes, how do we generate image that is by construction inside the constraint set? Because if you just randomly generate image from diffusion model or a scratch from the internet, then most likely it will not be inside the constraint set, because if we have many constraint sets, that most likely one of them will be violated, and then we're going to reject the image.
May I ask one last question while we are at it? Is it necessary to define the constraint set with 2 inequalities instead of just a half space? So, and if you are defining it in that way, is the distance, like the permittable distance from the hyperplane, the same in both directions?
Right. Okay. So this is a very good question. I'm missing some of the detail here, which I would cover when we go through the paper. But to answer your question, there are some technical requirements in order to construct like the mirror map that I will introduce later. And the requirement is that we have to use like this lower bound and upper bound, and we also require like these AI to be orthonormal with respect to each other, or at least it should not like it should not degenerate in a sense, right? So I cannot have like a duplicate normal vector. So it doesn't have to be orthonormal, but it has to span like it has to fully span the space. That's more of the technical requirement, and the upper bound and lower bound is also part of the technical requirement. And if those requirements are satisfied, then we have a nice convergence between primal and dual, which I'm going to talk about later. But yeah.
Okay, thank you.
Okay. Is there any other question before I continue?
Let's go.
Okay. Right. So the third reason is, as I just explained, these hyperparameters are actually useful because it can serve as token that is private. And then for a reason that will be clear in the next slide, another reason that we consider these constraints is because it is convex. So the convexity brings a lot to the table. So now we have a watermark framework that kind of meets all our desired property. It's invisible, it's induced very low statistical error, and its function as a private token. So the remaining question is how to generate image that always satisfy this constraint set. in other words, our remaining goal is to develop a diffusion model tailored to this constraint domain. And the primary prior method for this purpose is the reflected diffusion. And as the name suggests, it reflects the diffusion process whenever it hits the constraint boundary, as shown in the left figure. The main issue, however, is that the score function of reflected diffusions is intractable. So prior work either has to approximate the score or using implicit score matching. And in either case, the training of these reflected diffusion become less scalable. And so now let us revisit our convex constraint set. The convexity here enables a very interesting mathematical tool called the mirror map. And essentially, mirror map is a nonlinear but bijective mapping between primal and dual spaces. While the primal space is constrained, the dual space is simply an unconstrained Euclidean space. So you can imagine that we can define a so-called mirror diffusion model that learn the dual space distribution with all the desired property with the tractable score function, and then we can apply the mirror map to generate image inside the constraint. And here is an example of how mirror diffusion generate sampled inside a 2D ball constraint by learning its dual space distribution. Okay, so combining what we have so far, we can design a training pipeline for mirror diffusion as follows. Given a training image, we first project the image to the constraint set so that it is watermarked. And then we will apply the mirror map to get the dual image in an unconstrained Euclidean space. Notice that we use the gray dashed line to separate between the primal and the dual spaces. We will repeat the same procedure for all the training images, and then we get a data set of dual images that represent the distribution in the dual space. And from this point forward, the remaining training is identical to standard denoising diffusion model in Euclidean space. We will apply the same reparameterization, the same score matching laws, and etc. After the train, yeah, there's a question.
Yeah, if I can interrupt you here, could you go back one slide, please, where you, because this introduction of the mirror map and then how we go from the primal to the dual space.
Is it here?
Yeah, sorry, it's exactly here. So you said, okay, we have a convex structure, and then why does it follow we have a mirror map? And what is this mirror map in the first place?
Right. So I guess I'm skipping too much detail, but so for every convex constraint set, you can define a mirror map. So the mirror map is not unique, but you can define some mirror map such that so the mirror function is like the function phi that I call here, and if you and then the dual space is defined as the gradient map of the mirror map, where the input is the original constraint primal space. Right? I mean that's a definition, and one of the interesting property that people study mirror map or like the mirror Langevin dynamics for constraint sampling is because the dual space sample lies in the unconstrained Euclidean space. And I think one way to visualize how the primal and dual spaces is that like you can consider maybe like a very simple example where I only have like I'm in 1D and the interval is like say -1 to 1. And the mirror map essentially is modifying or changing the geometry of the primal space such that when you approach the boundary of 0 and -1, I'm going to stretch the space toward infinity, so that in the dual space I will never across infinity by definition, and therefore the corresponding primal sample will by construction always like not exist the boundary. So that's my intuition of understanding that. But I mean that it's one the example, but you can extend that to higher dimensional. But essentially, I'm scratching the geometry around the boundary such that I can do like unconstrained. I mean that's one of the way that Mirror Langevin do the unconstrained sampling. Mirror diffusion is different from Mirror Langevin. We only take the part of the mirror map for our users because we don't really care about the intermediate trajectory. But for Mirror Langevin, there are stricter like mathematical definitions on how these things should be constructed. And the problem is also different because for Mirror Langevin, usually it is applied for like the unnormalized sampling. So cases where you have the target density, but only up to some unnormalized constant. But it's really different. But I hope that
we will get into some examples of mirror maps later, I suppose.
Yeah, that's right. Yeah, because
yes, sorry, I just wanted to ask regarding the next slide. I just want to understand the training here. Is it done with the normal gradient descent or with this mirror gradient descent?
Okay, so that's one of the difference between Mirror Langevin and Mirror Diffusion. So for Mirror Diffusion, the only things that we took from Mirror Langevin is the mirror map. So everything inside the dual space stay exactly the same as training standard denoising diffusion model. And because of that, to answer your question, we use standard optimizer, gradient-based optimizer to train those models. So like say Adam W or not the kind of mirror descent that
So essentially the mirror map is maybe parameterized, but it is not learnable. You just apply it before on all images.
Right. So I haven't tried learning the mirror map. I think it is possible, but I didn't try that because like you can define a parameterized family of mirror map that did the job, and then perhaps you can simultaneously learn the parameter. So for all of our experiments, we predefine the mirror map.
Okay, thank you. I get it.
Guys, let's also
and
remember,
I'm going to go ahead.
With our questions, let's remember that we're like supposed to have at least skimmed the paper, right? And have a rough understanding of the paper. But yeah, let's continue.
Right. So I have like 2-3 slides remain, and then we can maybe dive into the paper. So for the slide here, I don't have the exact formulation for the mirror map, but that's going to happen when we go into the paper. Right. Okay. So let me continue if there's no question. Okay. So maybe just to give the summary again, for each image, because the training image is not necessarily inside the constraint set, so we have to do a projection step to make sure that is true, and then the watermark sample is inside the constraint set, and it's a valid primal sample, so we can use the mirror map to map that into the dual space, so that we can construct a distribution of sampled in the dual space. Then, because the dual space is simply in Euclidean space, we can apply a similar denoising model to learn the dual space distribution. And after training converges, we will simply apply the inverse of the mirror map, so that we can generate image. We can generate image in the primal space, or in other words, generate image that is watermarked. So here are some example of the watermark images generated by a mirror diffusion model. On both FFHQ and AFHQ, the generated image looks identical to standard images, despite that all of them are watermarked. We can also evaluate mirror diffusion on conditional watermark generation on ImageNet. So here are some example of ImageNet with resolution of 256. Specifically, we consider the JPEG restorations, where the goal of this conditional sampling is given a degraded low quality images on the left, we want to restore their corresponding clean images in the middle. And the result, this is the result of mirror diffusion shown on the right. So again, we see that mirror diffusion can successfully restore the clean images, but at the same time also watermark these images.
So all you do here is you have a diffusion model that you like can condition on some other image already, and then you like you have a diffusion model that you can condition on degraded images to generate these clean images, and then you additionally apply your constraint thingy and generate images that are in the constraint set and are thus watermarked.
Yeah, so I guess the watermark or the constraint thing here is kind of orthogonal to other approaches that, or like application ways that we have for diffusion. And so that means that we can easily embed it or like integrate these constraint set or the watermark to other models, which it's a good advantage. That's pretty much the end of the slide. Let me reshare.
There we go.
Okay, so you can still see my screen, right? Right now I'm in the paper. Okay. So for the remaining time, I think we can quickly go over the paper. In particular, there's a huge portion that I skipped, which is how do we construct those mirror maps.
First, can we maybe, before we get into those details, can we have a look at your loss?
My loss?
Yeah, up there, right?
You mean
have this?
You mean the training loss?
Yeah, it's somewhere above, I think. Yeah, there. No, down.
Oh, so this is not the training loss.
Oh,
right. The training loss is here. I mean,
yeah.
It's the same training loss that we have for diffusion.
Sorry about that.
I have notation wise, Y denote the dual space, and X denote the primal space. So it's maybe a little bit different from what you have.
Yeah.
But yeah.
Oh, and maybe you can just make your latent diffusion model analogy here as well. I think that might be helpful for some people.
Right. So one other way to see or like to understand mirror diffusion is that you can view that as a specific type of latent space model. So latent space model in a very general sense is that we want to move sample from the original space to some other alternative space that has more structural advantage for interpretation or like for training purposes. And in that sense, mirror diffusion is one type of latent space because we don't really want to we want to avoid directly learning distribution in the primal constraint side because we lose lots of property that makes diffusion model scale, right? So especially we don't have the tractable score, so the training has to be approximated. We have to use implicit score matching. We have to do simulations. So all of those are properties that we want to avoid. And the way we achieve that is by moving all these things to a latent space which is defined by the mirror map, and it's because it's become an unconstrained state space again. Everything that can be carried over from similar diffusion. So really, I think the key computation here is the transformation between primal and dual. So I have to apply the mirror map, and I have to apply the inverse mirror map to transport sample between primal and dual. And ideally, I want these transformation to be fast, parallelizable, and preferably like has closed form solution. So I don't want to really solve because the original definitions of like the mirror map is defined as equation 6, and we want to exploit some closed form solution between the mapping here for some constraint set that we are interested in. And there's a assumption or like the limitations of mirror diffusion, which is these constraint sets has to be convex. So that's the definition of the mirror map, but that's also a limitation of mirror diffusion because like we can do very scalable tractable training, but only on convex constraint set. However, I will argue that most of the constraint diffusion model, so let's say like for the reflected diffusion, most of their experiments are actually convex constraint set. So the convexity here is something that I feel like it's not being taken that serious or like emphasized that much in the prior model. And here we are trying to leverage this convexity so that we get a tractable model.
Yeah, well,
I hope that's clear.
of course, there are many applications where, like for example, for some molecule stuff, if we want to stay on the low dimensional manifold of low energy structures, or always within some, oh well, no, we could do some bond length cutoff, and yeah, but the manifold of 3D structures would not be like you could have convex coordinates and like convex constraints in internal coordinates or something, but the the constraints in this is actually a cool idea, right? Oh, yeah. So okay, let me not get into this for normal, but if we have just 3D coordinates and these 3D coordinates lie on some low energy manifold, then this wouldn't be convex. Okay, but right now we have this dual map. We have our mirror map, and we have the dual of the mirror map, and
Right. So
I get that we need those for training, and we need those, sure. But then when you write down your stuff down there where you make your examples, there you also have the Laplacian of the mirror map. So why do we need that?
Oh, so I guess you mean the Hessian of the mirror map. So the Hessian of the mirror map is needed on, yeah. So where is it?
Down.
Oh, it's here.
Down.
Right here. So another advantage of mirror diffusion over reflected diffusion is that for mirror diffusion we can derive the tractable variational bound because we know the variational bound for the diffusion in the dual space. So the part that is missing is like the transformation between from the dual space to the primal space. And in order to compute this additional term, which is shown in equation this term in equation A, we will need to compute the Hessian of the mirror map, and that's why so this is not required for training. If you don't care about computing these vertical bound, then the computation on this Hessian is not important. But otherwise, we also provide analytic expressions on these. So in the paper, we provide a few popular convex constraint set and how these constraint set can like what kind of mirror map that we can use for those constraint set. In particular, we consider 3 convex constraint set: the ball constraint, the simplest constraint, and the polytope constraint. So the polytope constraint is the same as the watermark constraint that I presented in the slide before. So and the ball constraint is, if you recall that I have a simple 2D example of how the mirror diffusion works, that is the ball constraint. And I showed the example in 2D case just for visualization, but all of our computation can be extended to arbitrary dimension.
Yeah, so we only need this if we want to evaluate likelihoods, and we only need it to at the very end, like once. We need to evaluate this once for generate example.
That's right. Yep, that's right. That's right. Cool. So then I'll just briefly go through the mirror map. The first one is the L2 bore, where the constraint set M is defined as this inequality. We can construct the mirror map using standard log barrier function, which is defined in equation 10, and then all the mirror map and the inverse of the mirror map and the Hessian are given in equation 11. So we have a derivation in appendix, but I don't think that's very important for the presentation. The thing I do want to highlight here is log barrier is a very common mirror map that people will typically use. In most cases, log barrier mirror map does not admit closed form solution for its inverse and Hessian and etc. The L2 ball here is a special case that where this log barrier function happens to have an analytic inverse. So this is what we are leveraging here. That's the first type of the constraint set. And I think right. Okay. So if you look at the figure on the left the 2 figure on the left hand side, these are an example of how the primal samples and the dual samples for the mirror map that I just shown. Like you can see that it has similar pattern, but potentially when the sample are near the boundary, it can be scratched to much far away. But essentially it's an unconstrained space. That's an example.
There's nothing expensive in what you just showed, like in these mirror maps at all, right?
What does it mean?
No, there's no expensive computation in the mirror map at all.
Right, that's right. That's yeah.
So,
because all the things here are parallelizable, both across the sample, so both across the mini batch and also across the dimension wise. I have a computation. I have a complexity table at the end, but
yeah, but you have like this 108% of compute time compared to DDPM. But where does this, like, where do these 8% come from?
The 8% come from the fact that we still need to map samples from the primal to a dual, right? So
but that seems like these computations here, they shouldn't take any time at all, it seems.
Perhaps I can improve my implementation, but I mean that's the only source of source of implementation.
Oh, anyway, it's not a bad problem to have.
Yeah, that's relatively cheap. and I think I select the worst case. I report the worst case scenario for the table. Otherwise it's just pretty much exactly the same, and I feel like that
Yeah.
might irritate reviewers. But yeah.
And do you have some, like, might there be some concerns that somehow the space that we're in is otherwise ill-behaved, or it's not so, yeah, it's kind of, it's, are there reasons to believe why generative modeling in this space should be hard?
In what space?
In the mirror space of, like, let's say the simplex. If we have the simplex and the mirror space that you define there, does it have some uglinesses that, like, if we get, for example, to the close to the border, right, then the
Yes.
gradients
That's
blows up.
yeah. That's a very interesting and good question. I think that depends. For low dimensional example, I think diffusion model should be fine. You may have to play around a little bit with the architecture, because most of the diffusion model, I mean, like if you adapt the architecture from the image generation diffusion model, then the implicit assumption here is most likely the sample will be within some, like -1 to 1, right? Because right now we have a fully unconstrained state space, the dual space sample can potentially go to very large value. So you may have to add some normalization layer to your architecture to handle those regions. That's the first thing. The second thing is the distribution. The dual space distribution will get pretty ugly, especially around the boundary, because I'm stretching the boundary in the primal space, right? So the samples may be very far apart from each other in those regions. And you can imagine that if you have very few samples in the boundary, that will make the learning even worse, because you're not going to match exactly, I mean, at least in those regions. However, because when I apply the inverse of the mirror map and stretch everything back to the primal space, those distance will like the discrepancy between the learning distribution and the true dual space distribution in those regions will be will become smaller when I map everything back to primal space, because I'm collecting all the geometry, in back to the original small region. So at least empirically, I don't see a huge issue in terms of learning things at the boundary.
Yes, so two questions.
You may require some, like, say, maybe the way we sample maybe the way we sample the time step should be different in the dual space. That will be an interesting things to try, which I haven't done in this paper, because I think we achieved reportable result by using the default parameter. So we didn't move on to those here.
Okay, then like, how much did you have to play around, and how much did you have to change in your watermark experiments from a standard diffusion model to your watermarked diffusion model, where you have the constraint set included?
So for the image watermark, we use pre-trained model from the
Yeah.
like the standard diffusion model. Yeah. So the dual space, the dual image, I don't have the visualization here, but it's not that. I mean, it still look like a valid image, so it's
No,
not
no, no.
that
I mean, I don't care about what it looks like in the dual space. I mean, like, did you literally just implement your different training procedure, and by applying the dual and disapplying the dual? No, but, well, just by applying the dual, for training, you only need to apply the dual, right? And then it straight up worked, or did you have to play around with the schedule, or you had to play around with the architecture or something?
Pretty much just plug and play.
Good. Okay.
I have to play around with the constraint side, but that's not what you're asking.
Yeah. And then another thing is, maybe if we now have, let's say, categorical data that we want to generate, and we're on the simplex, we want to sample something on the simplex, then our samples will all be in the corners, and they will be on the boundary. So will this be a problem at like low noise scales? For the score at low noise scales? Yeah.
I think there will be a problem, but I mean it can be easily fixed by how you generate your simplex distribution, right? So you can always add some noise, as long as when you take the softmax, it still give you the correct category. Then we can treat that as an alternative, and then we can apply mirror diffusion on learning these. That will resolve some of this instability when samples are exactly at the corner, because when samples are exactly at the corner, the dual sample will just explode.
So you would say in that case, don't train with your categorical data on the simplex. Instead, add a little bit of noise to it, take the softmax and train with that stuff.
Yeah. That'll be my suggestion.
Okay. Cool. Then, very nice. Let's continue.
Right. So that's the bool constraint. We also have the simplex constraint. So simplex is a special case of the polytope, and the mirror map that we use are borrowed from the Mirror-Luntman dynamics literature, where typically they use like this kind of an entropy function to present the mirror map, which is given in equation 12. And so there are like very rich analysis in those areas for how the inverse and the reverse, the standard mirror map can be constructed, and also the Hessian. So which are given in equation 13. One things that right, I mean that's pretty much it. And the thing that I think is more interesting is the polytope. For the polytope, we can still define a standard log barrier as equation 14, and then we can define, and then we just simply take the gradient, then we get the mapping from the primal to dual. The problem here is that there is no analytic solution from dual to primal. So the inverse of equation 15 is like does not admit closed form solution, and that's like one of the issues for the log barrier function. For the L2 bool, it just happened that the inverse is tractable, but for here we are in a more general case. So we have to do additional modification in order to proceed. And the things that we did first is that the inverse is tractable. It's kind of tractable if we make all the constraint like the normal vector to be orthonormal. So if all the normal vector is orthonormal, then you can write something like the 16, where the only things that remain unknown is this Si minus 1. So the inverse of Si is shown in figure 4. So in on the left figure of figure 4, this is the mapping between primal and dual for the log barrier, which is the function S here. So so you can imagine I can simply construct these monotonic function, and I simply build up some lookup table or doing some interpolation and then I can get some approximations of these S, the inverse of S, and then I can proceed with the polytope constraint. The problem, however, is that I think it's pretty obvious that these function SI is it's kind of unstable because in most of the region it stay pretty much the same, and then especially at the boundary it will be stretched very fast to the infinity. So we did some modification by changing these S function from the left hand side to the right hand side, which is implemented by an hyperbolic tangent. And the intuition here is that as long as the function is monotonic increasing, meaning that there's always a one-to-one mapping between primal and dual, it serves as a valid mirror map for training purposes, and that like reduce the training instability that we observe in practice. And so so the final form is given. The final form is given in equation 17 and 18. We have a few other simplification, but that's pretty much how we implement the watermark. So and then finally, here's a complexity table for each constraint set. Everything is very scalable for the polytope because we have to compute the orthonormal vector. So we have additional a factor that depends on m. So m is a number of the hyperplane constraint. Usually m is set to like around 100 for all of our image experiment, which didn't really take much time. And it is possible to extend the polytope constraint to orthonormal as long as it is as long as there's no duplicate or there's no degeneracy in the constraint set, which we kind of give some remarks in here. But all of our experiments we use orthonormal normal vector.
Okay, so would be somewhat now first, can you come up with some other types of data where a polytope would be a constraint set, or types of problems where the polytope would be an interesting constraint set?
I guess that's like say for example, if you are working on the opinion modeling or the opinion dynamics, in their literature, I mean, it's reasonable to assume that the opinion is bounded, or it's being normalized to some region. I have seen opinion constraint to be either like the polytope. It's kind of like the box constraint, right? Or it could be like a bold constraint. So I think I've seen both. Right. I guess. Yeah.
What happens if I have a ball in a two-dimensional ball, and yeah, and I say I wanted like only half of the ball? Can I then still use your simplex? Can I still use your map that you have for the ball?
That's a good question. I am not sure actually, because I mean, so we can compose all the constraint set that I presented here. Compose in the sense that you can apply different constraint set to each dimension. but I think what you are asking is that I want to have the I want to have a constraint set that is a union between bool and maybe some polytope, such that it's only half of the circle. Will require some thought and computation. I mean, you can always construct a valid mirror map by applying the log variant, the log barrier. The problem is always how do we get the inverse, and so the inverse is required when you do the generation, because we have to apply that at the end of the generation to map from dual to primal. That being said, it will not affect the training complexity, because for training I only need one direction, and one direction is always easier to construct. So in the worst case, I'll need to spend additional time to solve in generation, so during the inference, but that won't affect training.
Yeah. Okay. Nice.
Okay. I guess it's pretty much about time. So I just go through some of the experiments, especially for the constraint generation. So we have some numerical comparison between other approaches on bool and simplex. So here are some visualizations of like the comparison between mirror diffusion and the reflective diffusion on modeling the simplex distribution.
Yeah, but I mean, also wait a second. Like this is a kind of this like okay, I guess MDM gets it quite right, but this is also extremely toy, right? And we're just overfitting a Dirichlet distribution here, right?
What do you mean by overfitting?
I thought we like what we do here is we have a single Dirichlet distribution and we sample from that, and then we train a diffusion model for that on those samples. Yeah, and this
Right,
should be like a very easy task.
Right, because for the constraint, I mean, for those experiments, we use synthetic data set. So those are not real world example. The real world example are left for the watermark. So
yeah, I'm just saying like how bad reflected diffusion is here, even for this simple task.
Yeah, so reflective diffusion is not that good. I think mainly because they use implicit score matching, so it's make the framework not that scalable. I mean, even in 7-dimensional, you can see a difference, and it gets worse when you move to higher.
What's this sliced Wasserstein metric? Is this like some distribution? Yeah, okay, so you take some slices and then you calculate the Wasserstein distance between the distribution on those slices?
Right, so slice quotient is a slightly more robust matrix when we move to higher dimensional. So but I have other matrices, including the Washington one in the appendix. So I just shown here. Like I have other matrices, and the trends stay the same. So the main takeaway of table 3 and 4 is that compared to model that was designed for the constraint domain, we have better performance. And compared to standard DDPM, like the standard diffusion model, I mean, we achieve similar or better performance than DDPM, but without violating the constraint. That's the main message that I want to give. And then
so right, we can also just use our DDPM as you like. What you also do here is just train a DDPM on the same data, and yeah, sometimes it violates the constraints, but if we, for example, want to generate discrete data on the simplex, then this is also something that we can do, and this is then would then basically be something like
That's right. Yeah, that's right. So this is always like a strong baseline, and I think most of the constraint, well maybe not most, but some of the constraint diffusion model kind of ignore this comparison, and I just want to include it here to highlight. So that's depend on what you need, because if I'm okay with a little bit of violation, I think everybody's. I mean, we are free to use DDPN, but there are some cases where these become really important. I really want to ensure there's no violation. For example, in the watermark, then mirror diffusion will be a good alternative. Yeah.
Can I ask a very basic question, but about the watermark? So now, if you want to check an existing image for the existence of the watermark, what exactly are we doing? We are transforming it into dual space and estimating likelihood?
So in order to check an image, like whether or not this image is watermark, we simply check if the image is inside the constraint set, because inside the satisfy the constraint or inside the constraint set is equivalent to being watermark, right? So I only I already have all the hyperparameter of like the normal vector and the interval, so I simply just check if all the requirements are satisfied.
Okay, so this is in the primal space, not dual.
Yeah, so I don't need to yeah, that's
yes,
right.
but then the question, how hard is it to train a model that would fight the watermark that is produced by your model, that is like watermark removal model? How hard
can you say that again?
How hard would it be to train a watermark removal model that produces the same image but without watermark?
And you say by training, you mean like
so okay, like in general, the idea of a watermark here is that if I understand correctly, it is that you just produce some images and then you can certify them. You can make sure that they came from this particular model, right? And the adversarial example would be if somebody just wants to remove a watermark. Or is it not a problem at all, and you can remove it just by altering any pixel?
This is a very good question. I think there are. I mean, you can easily come up with lots of adversarial agents that try to remove the watermark. But I don't think, like, say, alerting pixel will be sufficient, because the watermark is constructed by all these unknown noises, right? So you either have to have some mechanism that wash out these unknown noises. Otherwise, it's hard to generate. I mean, it's hard to generate or like duplicate watermark images. That will be my guess.
Okay, I understand. So basically, it relies on the complexity, I think, of the original constraint set and the fact that it is unknown to the attacker. But okay, thank you.
Right, that's right. Yeah, that's right. Thanks.
Yeah, hello, Guan. Thanks for the presentation. Is it the right time to ask some like high-level questions about the work?
Sure.
Yeah.
Sure.
Cool. One thing I wanted to ask is if it's possible to separate the watermark from the image and have just like visualize the watermark, what it looks like, or it's not something that's possible? It's really like difficult to separate them.
Oh, sure. It is definitely possible to visualize what is being added. I mean, because we have this computation of primary and dual. So if I subtract dual from primal, then I can visualize what the watermark would be. I haven't done so, but because those are constructed by like the high frequency noises, I think it will be very similar to adversarial example. So that would be my guess. But
Okay.
we are going to release code in hopefully at the end of November. So you can. I'm hoping to release code before New Year's. So let's see.
After
Yeah.
after rebuttals.
That's right.
Yeah, cool. Like, it'd be nice to see what the watermark looks like. Does it look like noise, or does it look like something similar to the image? Like if you have an image of the bird, like does the
Right.
watermark also look like a bird so that you overlays on it and things like that?
Right. It should look like noises. I try something similar to the second option that you mentioned. But because the watermark is applied uniformly to all the model, all the images in the training set, if we apply the kind of like bird-like watermark, then it will affect the image on it will affect the rest of the image, and you will see that. So in practice, one way we select the way we decide these hyperparameter is by first have a guess of how those parameters should look like, and then we can go through the entire training set and see if the watermark images make sense. And that can be either done by just plotting the images, or we can compute like some numerical values such as the FID in order to make sure that these constraints that will not really this constraint set does not affect the generation quality that much, because you can imagine if I if I learn a perfect diffusion model, then at best I can generate at best the image I can generate are those watermark training images, or like those watermark images. So and because I have access to those, I can compute the FID so that I know the upper bound of the performance.
It wouldn't surprise me though that like if you had a random noise, but you could still see a shadow of something in the random noise. Maybe not. Maybe it's like adversarial attack where it looks exactly like random noise, or maybe it's blends into the image in some different way. And here like the watermark is only detectable from the original model that was trained to produce the watermark, right? Like someone cannot try to predict whether the image is watermarked. Okay.
So that's right.
What about like robustness, for example? Like you mentioned at some point reconstructing JPEG compression, but what about robustness to JPEG compression? Like someone could just take an image, if it's random noise, you apply a mean filter, a median filter, or any kind of like basic thing like JPEG compression, and completely destroy the watermark. No?
Yes. That's one thing we have been looking into. Yes.
Yeah. So any ideas on how to make it proof to that, or like there's no way to watermark in an invisible way?
Right. Yeah. So I think these all boil down to how to design the watermark, or like the constraint set. We use high frequency noise. I mean, we actually tried both. So we tried high frequency and low frequency, but low frequency is not very suitable for images. It will reduce the generation quality by a lot. So we end up using that one. But but the disadvantage of high frequency watermark is that it can be easily washed out if I know this is a like I can use some low pass filter, then I can destroy those watermark. So I think maybe a good alternative is some mix between low and high frequency. We may want to have a majority of constraint being high frequency so that we can achieve a low false positive rate, but maybe a few other constraint that will not be easily washed out by these low filtering, and we can still use that for some detection purposes. That would be my current guess.
But yeah, if the majority of the watermark is a high frequency, still get destroyed. It'd be cool to see, like, for example, like one way to to do this kind of watermark is like imagine on every image that you have trees on it, there's a tree of a specific shape that gets produced somewhere in the background that's unnoticeable by anyone because it looks like a real tree, but it's a tree that has been generated by the watermark.
Right.
So like this is kind of a blend of like low frequency, high frequency, but even with the JPEG compression, you can still get that. But the problem is that not all images have trees. So how do you make a watermark like that would work in every case possible? Like, and that becomes a big problem.
Yeah. So making watermark kind of data dependent, it's for sure more powerful. The constraints that we presented here are kind of not data dependent in a sense. So
but can this be done with latent, combining this with latent representation? So like you first do encoding into latent space of the image, and then you do your dual representation, dual mirror map. Would this help?
That's also possible, and I think there are some prior work that embed watermark in the latent space instead of like the image space as we have here. But I feel like it's unclear how I can still apply manipulation on the primal space, and it's unclear how that will affect the latent space. If the latent space is like remain unchanged with respect to those modifications in the primal space, then that will be a good alternative, and maybe we can apply like the mirror diffusion in those latent space. I don't see any issue.
That would be cool. Another follow-up question. So what if you generate a library of generated images with watermark, and you train another diffusion model on these images? Will this new diffusion model generate watermark, like just because it has learned from database, like or it is too subtle even like for a diffusion model to get these watermarks?
I don't have a clear answer for that. I will guess that it will be I will guess that it cannot reproduce all the watermark.
I would be very surprised if it can. Like, right, we have this very low dimensional manifold, and like that our diffusion model can learn to really put data on that manifold. That would be surprising to me.
Yeah, I'm just wondering because like if there's a website that has all watermark images and someone else used that website as a training set for his own model, like will everything be watermarked, or like at least a percentage be watermarked? That's
But Guan, don't we sort of have an experiment like that you already showed us with your unconstrained, like the DDPM on the simplex, and we always have watermarked images that are on the simplex, But now if we have the DDPM that is just trained on watermarked images, then it's still in 20 dimensions, right? And we're only talking about 20 versus the million that we have for images. In 20 dimensions, it still falls off the simplex 68% of the time.
Yeah,
So
that's a good point. Yeah.
I think
We haven't tried that for image, but yeah.
Therefore, for an image, this percentage then would probably go to like 99.99. Like if you now go from 20, like the difference from 5 to 20 dimensions is like 10 to 70%. And then if we go from 20 to a million dimensions, then my suspicion would be very much that
yeah. But I think it's a interesting, like maybe it could be made more theoretical question as what are the data? So like say if I have infinite number of data from the watermark, I think maybe eventually I can learn those like am I able to recover the underlying unknown token if I have infinite number of these watermark generated image? But that's I don't have a clear answer for that. But
we have a question.
That's interesting.
Can training in the dual space help with rectifying flows of the diffusion models in any way? Do you know what's meant with rectifying? Like maybe making them straighter or something?
So if you're talking about like the rectify flow, like for distillation purposes.
Oh, wait a second. I think Denise just unmuted. Maybe Denise, you can clarify.
Yes. I was talking about this.
Okay.
Okay.
I don't think so. So I don't think so in the sense that I think what presented here is orthogonal to other approaches. So you can combine the two together, but I don't think the dual space itself is related to the related to rectifying flows.
Okay, yeah, that's was just a guess because of the convexity of the operation. Of course, it doesn't.
Oh, I see.
It doesn't make the space itself like
I see.
convex, right?
So
the data distribution. I mean,
right. So the convexity that was mentioned in the rectify flow, as far as my understanding, is to ensure some uniqueness when they apply these rectifying procedures, such that eventually it will convert to the optimal transpose solution. So that is a little bit different from what we have here, because what we have here is that the domain itself is in the constraints.
Yes, I understand. Thank you.
Convexity in rectified flows?
Well, I meant that the linear interpolation, right, that they are using to rectify their flows, it essentially means that the trajectory is convex, right? So
between the
between the noised image and denoised.
But what space are we even talking about here?
Yeah, but here indeed it is different, because here it is a convexity on the domain, and there it is a sort of convexity with respect to the flow that it's curl free in essence, at least as I understand it. But it's basically different things.
Yeah, it's more related to how they parameterize the drip, because they want the drip to be the gradient fill, so that remove like the rotation component, and that ensure that the map they get is the optimal. But that's different from.
I'm here once again, and also to have some dogs around the office. But if you want to join the next reading group session yourself, then all the information for that is down in the description. And also have a look out for the next week's discussion, where we will also have another paper by Guan.